Hello everyone, I'm going to present our paper called Security of Control Systems, Prevention of Aging Attacks by Means of Convex Robust Simulation Forecasts. This research has been conducted by Eric Zamay, Gérard Scorletti, Paolo Mazzioni, who belong to Laboratoire Ampère CNRS, Université de Lyon in France, and by myself, Cédric Escudero, who I belong to Laboratoire G-Scope CNRS, Université Grenoble-Alpes in France. During this talk, I'm going to present the control system security and the literature around it. What is an aging attack, the main result of our paper, an application on a DC motor, and we'll end the presentation with a conclusion part. Since 2 decades, control systems have started a transition towards the computerization of its components. It includes the controller, the network, the HMI, and so on. This computerization leads them to operate as a standard information system. Hence, they face similar vulnerabilities as the ones in the information system. Some attacks have spotlighted the devastating damages an attack could have in a control system. Among them, the well-famous attack Stuxnet revealed in 2010. Stuxnet attack have taken the control of an uranium enrichment facility in Iran. Also, Industrial in 2015 is considered as the first attack against an electrical power grid. It occurred in Ukraine in 2015, causing a blackout for almost 200,000 people. Besides, Triton in 2019 as targeting a petrochemical plant in Saudi Arabia. It consisted in taking control of Safety Instrumented System, SIS, often considered as sufficient to deal with attack, and as shown it is not. All these attacks share a common point. They compromise the controller or the network to forge a destructive control signal UFT. This is the so-called deception attack studied in the literature. Deception attack consists in altering the behavior of the dynamical system by compromising one or multiple control parts as defined in the literature. A wide range of methods have been proposed in the MOST to detect abnormalities either in the control signal U or in the measurement Y. Among them, methods analyze characteristics of the results of the measurements. Others, based on the control signal, are interested in forecasting the reachable set to guarantee the service delivered by the process. We propose to study a novel class of deception attacks, which consists in reducing the system lifetime through the control signal while maintaining the service delivered by the process. This is what we call an aging attack. To the best of our knowledge, aging attacks have still not been investigated in the literature. For example, the temperature increase in a machine or the power consumption of an autonomous system are aging examples. Our research interests deal with dynamical system modeled as affine time invariant continuous time system, as shown here, where X is the state, U is the input, A is the affine term, and big A, big B are system matrices. This mathematical model can be reformulated with X tilde, as shown here. Our research problem consists in restraining the input U of T such that stealthy aging attacks are prevented. This can be mathematically formulated as follows. Consider an input U belonging to the set big U and a state X belonging to the set big X. Find the maximal input set big U hat such that X belongs to a stealthy set big XS and big XS does not intersect with a dangerous set big D. Big XS is a stealthy set such that if X belongs to the set, the service delivered by the process is guaranteed. Big D is a dangerous set representing the abnormal aging of the system. To solve our research problem, we propose to use robust simulation. It consists in finding a bounding state set at a final time tf for a given set of possible initial values of x at an initial time t0. In comparison with another method based on invariant set, robust simulation method allows to consider time dimensions, which is an important feature to estimate the time at which the abnormality occurs. Also, no restriction about the stability of the dynamical system is required, which is required when you deal with the dynamical system without considering a controller. In fact, most of the dynamical systems are critically stable, which lead invariant set-based method not usable. So the main idea of the paper is an adaptation of the works in Bentala et al. In 2017 and Tobenkin et al. In 2011. Their work is based on the search of a time-dependent pseudo-dependent function. It consists in finding a positive definite function v such that v is strictly greater than 0 for all x different from 0, such that the first time derivative of v, denoted v dot, is less than or equal to 0. With q tilde, a time-varying symmetric matrix. As an interpretation, if v dot satisfies an inequality, then v defines a time-variant ellipsoidal double set from which the state trajectory will never go out. So consider the presence of a bounded input u belonging to the ellipsoid defined by the shape matrix R with center u bar. Then v dot is equal to the following matrix here. To make the search tractable, we have limited q tilde to the set of values polynomials. Then q tilde dot is its first time derivative. Recalling that we want to prevent stealthy edging attacks, we need to define the stealthy set. This set refers to the one in which if the states belong to it when the service delivered by the process is guaranteed. This set is defined by the ellipsoid with shape matrix big Xi with center Xi bar. We assume that there exists an input signal u of t such that x can belong to the stealthy set for any time t belonging to the interval t0, tf, and for initial condition x0. Since we want to forecast the state set over a given time interval t belonging to the interval t0 to tf, it is sufficient to constrain gamma of t being greater than or equal to 0 as follows. Also, for technical reason, we define the matrices shown here. Then, applying the well-known generalized S procedure on the constraints, it yields our theorem. If there exists m source q tilde z x, source alpha, beta, and a scalar epsilon, such that this matrix inequality and this one too are m source, then if a set of initial condition is within the level curve defined by q tilde at t0, then it will never exceed the level curve of the same value defined by q tilde of t for the given time interval. So m source is an acronym for matrix sum of square and source for sum of square. So for the reader who is interested, we invited him to go in the paper. From our theorem, we have proposed an algorithm for restraining the input set to prevent stealthy edging attacks, which is our research problem. First, we find the minimal bounding ellipsoid for the system over time interval t0 to tf for given input set we do it by maximizing the trace of Q tilde of TF by using our theorem. So it is a convex optimization problem. To give more freedom in the search of the bounding ellipsoid, we have divided the problem in n successive subproblems, in which we search for a bounding ellipsoid over the new smaller time interval. Then in second, we verify if and at which time t, Q tilde of TF intersects with the dangerous set big D. We model this set big D as the union of high number of half spaces. And finally, we restrain the input set such that D is guaranteed to be unreachable. So it is important to mention that the algorithms are called each other to solve the problem. So we invite the viewer to check out the paper to have more details about the algorithm. To find the maximal input set, we use a bisection method on the scaling term delta for R. So let's go on an application. So let us consider a brush DC motor modeled by the matrices A, B, and A, where x1 is the angular velocity and x2 is the current. And we define the dangerous set big D for I of t greater than or equal to 21.6 ampere and I of t less than or equal to 21.6. And here are the results. So by applying algorithm 1, the first step, it yields the left side figure. So here are represented the bounding ellipsoid at each 10 milliseconds for TF equal to 1 second. For all of the figure we have, the blue star represents the initial condition and the filled ellipsoid in red is the final bounding ellipsoid at time TF. So we can see that the bounding ellipsoid overlap with the dangerous set, which is here. Okay, so the dangerous set is here and here. And on the white side, we have the bounding ellipsoid for the computed restrained input set, such that the dangerous set is not overlapped, as you can see here. It is not. Hence, the aging attacks are prevented. Here, we have the same system and the same simulation, but we are working on stealthy aging attack. We have defined the set big C and the Xi bar. So we can see that we can restrain the input set such that stealthy aging attack cannot be launched. And here, this is the evolution of the hit time in function of the input set size. So defined with delta, the scaling term of the bisection method, at which the bounding ellipsoid overlaps with the dangerous set. So this is an interesting feature which could be yet helpful to trigger other detection algorithm. So one may note that at a certain input set here, the dangerous set is unreachable at any time t. To conclude, this work has shown how to analyze and prevent stealthy aging attacks by the means of robust convex simulation. In particular, it allows the determination of the time in which the abnormal aging occurs. This feature could be used for triggering, for example, other algorithms, and we could exploit the time dimension to establish time-varying input sets, which prevent stealthy aging attacks. Also, this work will be conducted in more practical cases. Thank you for attending. And if you have any question, you can reach me at my mail address. Thank you.